Hi everybody, today we are going to discuss effective sol gel method for nanoparticle synthesis. Basically, this method is transition of materials from solution phase, commonly called sol phase, to gelatinous phase, commonly known as gel phase. This process is an example of bottom-up method for material synthesis. This is a chemical synthesis method and it involves bottom-up synthesis. It means we start from atoms and from atoms we build up the nanoparticles. This is an oxide network formation via polycondensation reaction in the solution phase. So in this process or in this method, oxide network formation takes place through the process of polycondensation and the reaction takes place in the solution phase. The process is used for the synthesis of metal oxides and ceramics having high purity, also nanocomposites and inorganic as well as organic hybrid materials could be synthesized. So this method involves metal oxide formation as well as the synthesis of ceramics. Also, we can synthesize nanocomposites and hybrid materials containing inorganic as well as organic species. In sol gel method, hydrolysis of reactive metal precursors occurs, followed by condensation and polymerization reaction. So this method involves hydrolysis, condensation, as well as polymerization reactions. A liquid alkoxide, water as a solvent, and an acid or a base as a catalyst are combined. So in this method, we use a starting material, for example, a liquid alkoxide. Water is used as a solvent, or even we can use alcohol as a solvent, and an acid or a base is used as a catalyst to carry out this reaction. Metal oxide metal cross-links are resulted by removing an alkoxide R group. This is the oxide network formation process. These cross-links then condense to create a 3D solid network. So cross-linking occurs and cross-linked products further condense to create a 3D solid network structure. Metal oxides such as methoxides and ethoxides, aluminates, titanates, zirconates, and borates undergo hydrolysis reaction. So in this method, we can use a variety of reactants containing alkoxides attached with the metals, as well as we can use aluminates, titanates, zirconates, and borates. The alkoxide OR is replaced by hydroxide ligands. The process is called ligand exchange or hydrolysis. So hydrolysis reaction takes place, for example, in this equation, MORN plus H2O and water acts as a solvent here. So hydrolysis takes place, and hydrolysis is basically the breakdown of water molecule, And as a result of breakdown of water molecule, we obtain MOH OR N-1 product plus ROH, and alcohol is released as a byproduct. This reaction involves the addition of OH to the metal center M followed by elimination of ROH. This is a hydrolysis reaction. Different factors such as nature of the solvent, nature of the alkyl group, concentration of each reactant in the reaction medium, water to alkoxide ratio, temperature, and presence of acid or base as a catalyst affect the hydrolysis reaction. So hydrolysis reaction is affected by a large number of factors. These factors include the nature of the alkyl group, either it is methoxide, it is ethoxide, or even alkyl group with longer chains, concentration of each reactant in the reaction medium, as well as water to alkoxide ratio. Water is used as a solvent and alkoxide is the reactant. At temperature, either we are doing it at room temperature or we are little bit increasing the temperature, and as well as the pH of the reaction, either the reaction is taking place in acidic conditions or in basic conditions. Next is a condensation reaction. In condensation reaction, either alcohol or water is eliminated to produce metal oxide or hydroxide linkages. Condensation only occurs when the cation M is bound to at least one hydroxyl ligand. It means MOH species is necessary for the condensation reaction to take place. Condensation also occurs by oleation and oxidation. It means if there is oxide linkage or if there is oleation, then also condensation can take place. Oxidation involves the formation of oxo bridges MOM between two metal cations, and through the reactions we can show this process here. MOH plus HOH, HOH is water, goes into MOHM plus H2O, then MOH plus MOH, two species hydroxide attached with the metal center are reacting with each other, and we obtain the MOM plus H2O. MOM is the oxide bridging between two metal centers. Similarly, another hydrolysis reaction is when we use MOH, metal hydroxide, plus ROM. This also results into metal oxide metal bridging, but in this reaction, instead of water, ROH is released. Extended linear metal oxide metal chain polymers grow into three-dimensional solid phase networks in acidic conditions. So in acidic conditions, we obtain metal oxide metal chain polymers having three-dimensional solid phase networks. The acid-catalyzed polymerization takes place in three stages. Polymerization of monomer units to form particles. Next is growth of particles, Formation of chains are networks that extend throughout the liquid medium, which thickens to form a gel. This process is used to form films, fibers, and monoliths, different types of nanomaterials having different nature we can synthesize, for example, films, fibers, and monoliths. The basic hydrolysis results into a colloidal solution. The solid network is formed of rounded sol particles. To form a solid structure, the gelatinous material is further processed and solvents are eliminated. The trapped solvents or gases could be removed by drying at room temperature to form zero gels or under supercritical conditions, and thus aerogels are formed. So the solvents, for example, water or alcohol in which the reaction has been carried out, as well as this reaction goes on under air, so many gases are trapped inside the product, and we can remove the solvents or trapped gases by drying at room temperature, or we can uh, do this removal at a little bit elevated temperature. And at room temperature, the gel obtained is called zero gel. And if we remove the solvent and gases at supercritical conditions, then we obtain aerogels. This is the diagrammatic representation of salt gel method. We may take a beaker, glass beaker, and we add the precursor as well as solvent into the beaker. We do the stirring for a certain time, and stirring results into the sol formation. Then if stirring continues, a gel is formed that shows the connected porous structure, and then this gel is further processed, and if we apply supercritical drying, we obtain aerogel. If we process the gel through thermal drying, it gives us zero gel. And if we process the gel at low temperature by means of freeze drying, we obtain the cryogel. And all these uh, three gels, aerogel, zero gel, as well as cryogel, if these gels are calcined at higher temperature, for example 300 degrees centigrade, 400, 500 degrees centigrade, then these gels give us the solid product, and that is the final product. And this heating process at higher temperature in a furnace is called calcination. So again, if we start, so first reaction is the hydrolysis reaction, then second reaction is the condensation reaction. So first step hydrolysis, second step is condensation, and third and fourth steps are aging and drying. Aging means that we are further uh, increasing the process time, and drying means that we will apply some method to remove the solvents and trapped gases. And number fifth step, that the obtained product, the obtained uh, gelatinous product is further calcined and as a result of calcination, we obtain the final product. Also, we can see sol gel method through another pictorial representation, and we use the precursors. We dissolve the precursors in a glass container, and this way the sol is formed, and then the obtained sol we process it further. Sol solution as a source for spin coating. So that is the method of sol gel spin coating. In sol gel spin coating, whatsoever gel we obtain, we place the gel on the center of a substrate, and then we spin that substrate at a faster rate, and due to fast spinning of the substrate, and the gelatinous material is uniformly distributed on all over the surface of the substrate, and in this way we obtain a, a film of the gelatinous material on the surface of a substrate. Then second way of processing is substrate dipping into the solution bath, and in this way we when we obtain the salt solution, we dip a substrate into this solution, and on the surface of the substrate the nanoparticles are obtained. And third method is dry as a powder and calcination, and sol obtained is dried and calcined at higher temperature, and that result into a nano powder. This is also another pictorial representation of the sol gel method. We start from the metal alkoxide solution. We can do its coating on a substrate, and that coating result into the zero gel film. And if we apply the heat to this substrate, uh, we obtain a dense film on the surface of the substrate. Metal alkoxide solution through the process of hydrolysis and polymerization gives us a sol, and this sol is again coated, could be coated on the surface of a substrate. Similarly, uh, this sol is further through the process of aging. Its gelling takes place. It means the more condensed gel is obtained, called the wet gel. Then we do the process of evaporation, in which the gases, trapped gases, as well as the solvents are obtained. And through the process of heating, we obtain the dense ceramic material. As well as through the extraction of the solvent, we can obtain the aerogel. Similarly, from the sol, through the process of precipitation, we obtain the uniform uh, gel particles, but these are the basically colloidal particles, in which the solvents and trapped gases are present in the reaction medium. In a similar way, through the sol process, we do the process of spinning, and after spinning we pass the material from a furnace. A furnace means we apply the higher temperature to process the material, and as a result we can obtain the ceramic fibers. There are the certain advantages as well as disadvantages of the sol gel method. If we consider the advantages, this process is simple, low cost, and high yields could be obtained through sol-gel process. For the synthesis, normally we need a low temperature because whenever the sol is formed, basically at the stage of sol formation, we obtain the nanoparticles. But those nanoparticles remain in the form of colloidal solution. And if we do the further heat treatment or calcination, that steps are done to obtain the nanoparticles in solid form. Control of chemical composition as well as production of high quality NPs, of course, through this method. Ceramic nanoparticles, ceramic fibers, we can obtain different types of nanoparticles, nanomaterials having high quality, high purity. The process is scalable. We can do the process at very small scale, as well as we can scale up the process to several grams, or even by a proper uh, setting the reaction conditions, we can scale up the process to our requirements. Manufacture of homogeneous stoichiometric coatings and synthesis of organic as well as inorganic hybrid materials, control of coating chemical composition and homogeneity. Through this process, we can do the coating on a surface, and this is the specialty of this process, that we can control the chemical composition and as well as the homogeneous dispersion of nanomaterials on a surface using the sol gel method. Of course, there are few disadvantages of sol gel method as well. For example, this process requires long process times. Also, in case of raw materials, a few raw materials used in this process are costly, and that is a disadvantage. Overall, the process is low cost because most of the reactants used in this process are of low cost, but in a few cases, the cost of the raw materials is little bit high. Dear viewers, I hope this video is quite informative for you. Please subscribe the channel and press the bell icon, and I hope that in comments section you will give your valuable comments. Thank you.